Everyone. Choose any two icons. You're allowed to choose up to two icons. Any two, let me know. All right, let's see if you guys got lucky. Let's see how much your two icons are worth. Let's get a little. So add up how much money you get. Like if you chose 1 and 4, that's $2. If you chose like 2 and 6, 4 plus 8 is 12. Just add up how much money you got with your two picks. And let's see if that money will increase. I know the money seems a little bit, but as the game progresses, you will drastically get to increase the amount. Somebody chose 2 zeros. How can that be possible? All right. All right, let's go. Let's go. So this is a revision question from last week. Don't worry, I changed up the values. I need for you all to calculate the 4 missing values for me, right? So you're going to go back in your notes. You have to calculate 1, 2, 3, 4 missing items, right? You have to make the assumption that this is an ideal transformer, better known as a perfect transformer, because I explained last week that these formulas that I am circling only works for a perfect transformer. In other words, a transformer that's 100% efficient, which doesn't really exist in real life. But the majority of your questions in CXC will be regarding perfect, non-realistic transformers. Good luck, and I await your answers on the chat. So most people are sending this particular answer. First, power is just simply what? Current by voltage. So we have the current on the primary side and the voltage on the primary side. So we just need to multiply current by voltage on the primary side. And of course, that will give us the power on the primary side. So 25 by 115 is 2875. And you have to put the correct units, watts. Right? Because power is measured in watts. Right? Now, remember, in a perfect transformer, the power on the primary side is equal to the power on the secondary side. So without any calculation, you can make the assumption, if it's a perfect transformer, the power on the primary and secondary are the same. Right? I'm going to still give you all a minute to find IS and VS. But I am going to try to find VS first. So I'm going to use this portion of the formula, right? So I'm going to write it back here. VP on VS is equal to NP on NS. So I'm going to substitute any values here, right? VP is how much? VP is 115. VS, we don't know. NP is 1,000 and NS is 8,000. So you're getting 115 divided by VS is equal to 1,000 divided by 8,000. Now, before you attempt to cross multiply, won't it be easy just to simplify it? Like we know these 3 zeros will cancel out with these 3 zeros, right? Just to make life easier for you, right? So I will cross multiply with these now. 1 by VS is VS, and 115 by 8. 115 by 8 is 920 volts. And a lot of people sent that answer, right? So obviously now to find IS, you could use the other portion of the of the formula set over here, right? Remember, current is a little bit weird, right? For current, the secondary value goes on top, but the primary goes underneath. So for those who are a little bit lost, I'll give you a little jump start there to calculate IS, okay? Take half a minute and I'll complete the question. So this is clear the space here, right? So since we're using the other part of the formula, well, I box it off in, I guess, a nice purple, yeah? We're using NP on NS is equal to IS on IP. IS, we don't know. IP is 25. NP is 1,000 and NS is 8,000. 1,000 divided by 8,000, obviously the zeros will disappear. Right, so I'm just going to cross all these 3 zeros and these 3 zeros. IS by 8 is 8IS. And 1 by 25 is 25. 8 is a multiply, throw it across, you get what? A divide. 25 divided by 8 is 3.125 amps. Right? So quick question, is this a step up transformer or a step down transformer? Which one is this? Which value do you look at to determine if it's a step up or a step down? Do you compare the voltages or do you compare the current? Right. We're supposed to compare the voltage. The voltage tells us the name of the transformer, not the current. So let me just highlight it for you here. This is the voltage on the primary side, and this is the voltage on the secondary side. You all notice that the voltage got larger. This makes it a step up, right? And remember, current and voltage act as opposites. If voltage gets larger, you will notice your current. You can look at the values of the current. The current gets smaller. All right, so take down what you need to take down, and we'll be changing the slide in 20 seconds. Right, so I want everyone to draw this diagram for me, and please write the heading to the top. Let's assume it's 85% efficient. So I'll give you a few minutes, a minute to draw this out and wait on me, because this question has a serious trick in it. Transformer. So because this is not 100% efficient, it's not perfect. So I'm going to tell you what to do. Immediately you see these formulas, don't even think about looking at them. Those three, well, that you want to X off will not work for this transformer. The only thing that's going to actually help you is either this formula or this formula. Well, in 99% of the questions, this one will not even help you. It will be the red one that will help, okay? So everyone write down that formula, because that's the only formula that we are going to use. Here's how we do a question like this. The first thing you want to do is calculate the power on the primary side. So everyone do that for me. Power is just current by voltage. Super, super easy, right? 120 by 8 is 960. Well, I have to put watts, right? Current by voltage. Now, tell me something. Is the power on the secondary side also 960 by default? Is it also 960? The answer has to be no, because it's not 100% efficient. Only in a 100% efficient transformer, the power is the same on both sides, okay? So we cannot assume this. However, we could use regular boring maths to help us. 85% efficiency means that this refers to the power that only 85% of the power reaches the secondary side. So how do we calculate the power on the secondary side? If the full amount of power coming in is 960 and only 85% reaches on the other side, how would you do that in STA? How you find 85% of something? 85 over 100, and you multiply it by the something, which is 960. So everyone complete that calculation for me, right? How much is the power on the secondary side? Right, so that's an easy calculation. It's 85 divided by 100 multiplied by 960, which is 816. And a lot of people are sending that answer for me. Right? Easy stuff, easy stuff. Now, shouldn't it be easy to find the current on the secondary side? Because the examiner gave us the voltage on the secondary side. So remember this formula? Well, the only formula that we actually using is the red one. For the secondary side, we have the voltage, we have the power. Couldn't we use that formula to find power? Current, sorry. Current on the secondary side is power on the secondary side divided by the voltage on the secondary side. You all can more than finish that for me. Okay. Power on the secondary side is 1816, and voltage on the secondary side is 480. Right? So a lot of people are getting it wrong. I'm not too sure why, but I'm getting 1.7 amps. So this is 1.7 amps. For this question, right, you won't be asked to find NS. So that will be too difficult for CXC level, right? Because it's not a perfect transformer. So I won't bother to find NS because it's way off the syllabus. Okay. For the people who got 8 amps, a lot of people got 8 amps. Just let me know if you saw your mistake. It's just a simple division mistake, I'm sure. All right, notes time. Before you start taking down the notes, let me do a little bit of explanation for you all. I'll give you a time, right? So why are transformers not ideal in real life? Remember, it's not 100% efficient. And here's the reason. You'll remember this formula. Power is I squared R. Whenever you have any conductor, whenever a current, it doesn't matter if it's a piece of wire or just a piece of metal. Any conductor has a resistance. All conductors, okay? And whenever you try to move a current through any conductor, there's always some power loss. How do you calculate the power loss? Well, all you have to do is take the current, that the value of the current that's flowing through the conductor, and multiply, square it and multiply it by the resistance of the conductor. The point is, keeping it very simple, sorry. Once a current is flowing through a conductor, there will always, always, always be a power loss. Now, scientists are working on trying to create substances with zero resistance. It hasn't been invented as yet. But if you were able to create a piece of wire or a conductor with zero resistance, then the power loss, because I squared by zero, would be zero. That would be such an incredible invention. But like I said, they're working on it. Okay? So whenever current is remember, a transformer has what? Wires. And you're sending an AC current through the wires. So there will be power loss in the wires. That's the resistance of the windings. The windings is these red things. All wires, all windings must have a resistance. So you're going to get some power loss. Also, how does a transformer work? Aren't the magnetic fields from the primary side supposed to cut the secondary side? But there are millions and millions of magnetic fields. You really think all the magnetic fields from the primary side make it across to the secondary side? No, some of them go the other way by mistake. So not all the magnetic field lines make it across to the second side. That's a type of wastage. It would be nice if all the magnetic fields made it to the secondary side, but it doesn't. You call that flux leakage. Well, more specifically, magnetic flux leakage. Also, you will notice that they wrap the wires on an iron core. Isn't an iron core a conductor? And last time I checked, iron conducts what? Electricity. So some of the magnetic fields going to hit the magnetic core. And when just like how the fluctuating magnetic field produces a current in the secondary coil, it's going to produce a current inside the iron core. Yes, that's right. Current will be inside the magnetic iron core. You call that type of currents eddy currents. The person who discovered that named it after himself, right? And hysteresis. Remember, once you have a current moving through the iron core, you're going to get a magnet. So the iron core changes into a magnet. But here's the thing. Remember, it's an alternating magnetic field. At one point, here will be north and here will be south. The next instant, here will be south and here will be north because it's an alternating current. It takes work to magnetize it one direction, demagnetize it, and then switch it to the other direction. It's like this. You facing left, and then I tell you to face right. And I keep doing that over and over. Face left, face right, face left, face right. Doesn't it take energy to switch your position to what? Face the other direction? That's wasting energy, right? But it's something that cannot be avoided. So you call that type of energy loss, the magnetizing and demagnetizing of the iron core, hysteresis. Now, in the exam, you have to be able to quote all four and describe it. So I'm going to give you all 5 minutes to take down the notes. Let me know when you are finished. Okay? Let's go. And I think y'all deserve a little brain relaxer here, so you all know what to do. Choose 2 icons. Let's see if you get lucky. Any 2 icons. Let's see if we can bring up that amount of money. I think there are 2 zeros in this list. So if you pick and you get 2 zeros, today is not today. You can probably stay home. Okay. All right, how it looking there? Add up the total. Give me a total of how much you have in all now, right? So 6, sorry, which one was a bad choice over here? Number 10 was definitely a bad choice, and number 11 was a bad choice. So if anybody chose 10 and 11, I feel sorry for you. right? So somebody's up to $38. That's the highest so far, $38 in total. All right, let's go. Notes time. All right. So how do we reduce losses? Well, common sense stuff, right? If resistance causes power loss, well, maybe when you're buying wire to make the transformer, buy wire that has low resistance. The lower the resistance, the lower the power loss. Right now, this is a trade-off because the lower the resistance, the more expensive the wire will be. So you have to make a choice of an economic choice, in other words, right? So the point is, number one is common sense. Heat loss due to eddy currents. Now, remember I told you all, currents will end up in the iron core. And once you have current flowing in any conductor, you're going to get what? Power loss. So what did this do? Did it take the iron core and slice it into thin slices? So if you look at it from a top view, right? Let me say we look at it from on top. The iron core will look like a rectangle. What you want to do is slice it up like slices of cheese. And in between the slices, you put insulators. You call that lamination, right? So by laminating the core, you just end up reducing the amount of eddy currents. It's not perfect, eh? It doesn't completely stop the eddy currents, but it does a good job at making it less. So you can improve the efficiency by that. Right. Also, hysteresis, the magnetizing and demagnetizing of the magnetic core, just produce a lot of wasted energy. What you want to do is choose a material that can be easily magnetized and easily demagnetized. Usually that substance is iron. Never use steel. Never, ever, ever use steel. You have to use iron. Steel is hard to magnetize and hard to demagnetize, the complete opposite of iron. So in the exam, if they're asking for 3 ways of reducing losses in a transformer, I've already summarized the 3 answers for you. Memorize it. Let me know when you're finished taking down the notes. Let's go. All right. So what are the use? Well, what is the use of transformers, right? So transformers at the end of the day is a great invention and it helps you to save a lot of money, right? The thing about it, you'll notice outside your houses have transformers, and anywhere we drive on the highway and you see all of those electrical lines on the highways or crossing the highways, and you're going to see transformers all about. Transformers may be expensive, but they help you save more money in the long run. All of those electrical wires that run from power gen straight to your house. We're going to assume this is your house here. You live in a little mushroom house. All of those wires have a resistance in them. And once you have a resistance, you are going to get power losses. The whole country going to get power losses. And who has to pay that power loss? For that power loss? You, right? You will have. So here's what we're going to do. We're going to calculate the power loss for these scenarios. We're going to pretend we went back in time and the person who invented transformers, we told them, don't invent transformers. I mean, threaten them. So transformers will never, ever, ever invent it. Let's say that power gen is producing a voltage in the factory at 400 volts, and the current they are producing is 150 amps. Let's say the distance between power gen and your house is 5 kilometers. And this here is the resistance of the wire. Whenever you're buying wire, they just give you the resistance per meter. Okay? So the resistance per meter is 0.002 ohms for every meter. Now, I know that seems like a little bit in your head, but 0.002, what kind of small resistance is that? That resistance isn't going to cause much power loss, but you'll be surprised of how fast it adds up. So I want you all to do me a favor. Let's give it a shot. Using the yellow formula, I want you to calculate the power loss between power gen and when it arrives at your house. Just using the information and a little bit of common sense. Doesn't matter if you get it wrong. Just try. Good luck. So, how is power loss calculated? Well, I told you all, well, I advised you all to look at what? The yellow formula. How do you calculate power? Power loss. I squared, the current that is flowing, multiplied by the resistance. So let me write it here. To calculate the power loss, I'll put LOSS here. You take the current and you square it and multiply it by the resistance. All right, so we have most of the information here already. How much is the current? Well, the current coming out of power gen is 150 amps, right? So that's the same current that's going to be in the wires. So you have to take 150 and do what with it? Square it. But we need the resistance of the wire. Now, I give you the resistance in ohms per meter. How much is 5 kilometers? Isn't that 5,000 meters? Primary school calculations. So if every meter has 0.002 ohms, then the total resistance of the wire is 5,000 multiplied by 0.002. So let's multiply that out. 5,000 by 0.002. And I'm seeing 10 ohms. Now, I know that doesn't seem like a lot, right? 10 ohms? What a small value. So the resistance of the wire between power gen and your house is 10. Work out this, and you will see the large value you will get, right? The power loss is actually going to be very, very high. And it has to do because a high current is coming out of power gen, right? The resistance, I mean, the resistance isn't doing the majority of the bad right now. It's just that current, right? Right? Again, a huge value, right? 150 squared multiplied by, right? So I can't find squared button on my calculator. I'm getting this crazy value. 2, 2, 5 with 1, 2, 3. That's a crazy amount of watts. And remember, power loss, right? Remember, another way of measuring watts is joules per second. Remember, joules per second is the same thing as watts. So you know what this means? Every second that you use electricity, you are losing this amount of joules. That's crazy, eh? Because how much seconds it have in a day? Well, I can't remember, but quite a lot, right? So every second it losing that amount of joules. You can imagine how high your electricity bill would be if that was the losses there. So everyone take down everything. So we realize our errors, right? We should not have told the person who invented transformers to do it. So we take our time machine and we go back in time and we say, please, 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 please invent that transformer. We made a grave mistake. So the next slide is going to have transformers. Right? Let me know when you're ready to move. So let's look at a world where transformers have been invented. Oh, but before we go, right? So the genie appears. Choose one of the, well, I don't know if you all say vase or vase. It have three bars of it. I don't even know what the correct word is. Right? So the genie offers us three. Choose one. Let's see if we get lucky. All right, so people are sending in their choices. Let's see if you got lucky. The first vase, for people who chose the first vase, take all the money you have right now and double it, multiply it by 2. So that's a good one there, right? So the middle vase, oh no, it has a snake, a cobra in it, minus $10. So for the people who chose number 2, take whatever money you have and minus $10. Or should I say minus? Okay, no more jokes from my end. Okay, number 3. Multiply all the money you have by 3. Okay? So I guess the middle one was the worst choice. The last one was the best choice. Right? Let me know your total. Let me know your total. Let's go. So let's see a world with transformers. Now, for the transformers to calculate power loss, I only care about the current. I really don't care about the voltage. So you will notice that outside power gen, whenever outside power gen, there's a huge transformer. Before you send all of that electricity to the main power lines to go to your house, it has to run through a transformer. So here's what. Here we clearly have a step-up transformer. I want you all to calculate the current. I only care about the current that goes into the line. Use this here, a boxing off which part of the formula to use. Remember, this here is the primary value. This is the secondary value. You have the primary current, that's the current going in, that's just been produced by power gen. I am asking for the secondary current coming out of that transformer. Good luck, right? Oh, here, do me a favor. Well, and we'll do it after. It don't really matter. Just calculate the current coming out of the transformer. Yeah. Right. So remember, we have these values here. This 400 and 150 are primary values, and those are primary values. So this here is a primary voltage, and this here is the primary current. We're trying to figure out what's coming out on the other side of the transformer. So we're trying to find the secondary values, secondary current and secondary what? Voltage. So here will be secondary voltage and secondary current. But I asked you all to find the current first. So we're going to use this portion of the formula, NP on NS is equal to IS on IP. NP is 1, NS is 500. IS, we do not know. IP, we do know. It's 150. So let's cross multiply. 1 over 500 is equal to IS over 150. IS by 500 is 500. IS 1 by 50 is 150. throw across the multiply, get a divide, and lots of people got this. 0.3 amps, right? So the secondary current is 0.3 amps. Now I'll give you all a little bit of shortcut, right? I know I could go and use the next portion of the formula, but I'm showing you a little shortcut. You're not allowed to use the shortcut, but you can use it to predict your answer. Remember, if the ratio is 1 to 500, like once the first number is 1, it's really easy to predict what's going to happen. This is a step-up transformer. In a step-up transformer, the voltage will get what? Larger. And how much times larger will it get? It gets 500 times larger. Which means if the voltage is getting 500 times larger, then the current is getting what? 500 times smaller. So I don't know if you all saw this. And you could have just take the 150 and divide it by 500, and you would have get the 0.3. Because you know, since it's a step-up transformer, it's going to get the current to be smaller. How much times smaller? 500. So that means it will be very easy to kind of predict what answer we would get if we do the voltage calculations. The voltage is supposed to get how much times larger? 500. So if you take 400 and multiply by 500, you're going to get what? You get a 20 with 4 zeros. 1, 2, 3, 4. All right, so I just let you know. So how much people got? Well, real people got those answers. I don't really have a problem. The correct answers way outweighed the wrong answers today. Right. Do me a favor now. You think you can calculate the power loss? Remember what was the resistance of the wire? Remember in the last question, the resistance of the wire was 10 ohms. We had calculated it. Calculate the new power loss now. Calculate the new power loss. Power loss is current squared by resistance. Look at the new current now. Remember, the transformer took the very large current and made it really, really small. So calculate the power loss now. Right? I just need to erase a few things here. How much is the power loss there? Zero 0.3 squared by 10. You're getting 0.9 watts. Look how small that value is compared to the previous value. The last value was 2 million and something. This time the power loss, it didn't even make 1 watt. So you see how a transformer can save a country a lot of money, right? It saves you a lot of money. But we have a little problem. Remember, the values are going to be circling here now. I'm going to circle it in green, right? For you guys, so you can focus on it. These values are going to be sent to your house, right? Now, here's the thing. The current is not a problem. The current is 0.3 amps. I'm pretty sure your house could handle 0.3 amps. But guys, look at the voltage. 200,000 volts. If I send that voltage to your house and you plug in your phone to charge, what do you think going to happen to you? I think you're going to blow up. All right? Right. So that means that is why outside your house, it has another transformer. It actually has something called a step down transformer. Look at this. The turns ratio is 1500 to 1. That means the voltage will get 1500 times smaller before it enters your house. Okay? So anyone, without doing any major calculations, you think you can calculate the voltage inside your house if we use a 1500 to 1 transformer, a step-down transformer, we just making the voltage 1500 times smaller, right? Let's do a quick calculation and just send it, right? You can just do it mentally or just drop it on your calculator. Now, Cyrus, check it back. And you're just supposed to take the 200,000 and divide it by 1500 because it's making it 1500 times smaller, right? And I'm getting 133 and 1/3 volts, which is a safe voltage to have in your house. Well, safe enough, right? So that is why it is have a transformer before just outside power gen and just before your house. One is to raise the voltage and decrease the current, and the other one is to decrease the voltage and it will up the current a little bit, so it's safe in your house. Okay? So now you know the purpose of transformers. I know it's Carnival Sunday and y'all probably have big plans. Like as soon as class is over, you all have somewhere to go, right? So, all right. So we're not gonna have time to do all this. I need one more week with magnetism and electromagnetism. The next thing we're gonna do next week is Fleming's left-hand rule and a whole set of practice questions on it, and Fleming's right-hand rule and a whole set of practice questions on it. And then we will be finished with electromagnetism and magnetism, right? But that's a problem for next week, right? So I'm giving you all a 10 minutes off a little bit early, somewhere around there, right? So guys, enjoy your carnival. Remember, there's no classes on Monday and Tuesday, right? So enjoy yourself, be safe, have a good one. Right.